Hey everybody, another day of SUPA. Hope you're doing okay. And we are moving on. So last class we were dealing with intermolecular forces, and we dealt with the first three, and we talked about dispersion forces, dipole forces, and hydrogen bonding. Ooh, had a brain fart for a minute. There actually is one more intermolecular force, and it's a little bit different than all the other ones. So our fourth intermolecular force is one that we've actually already talked about. Molecule ion attraction. It actually has another name that you will see. It's also called ion dipole attractions. Same thing. So this is an intermolecular force because it's between a molecule and another ion. So it's between different things. So it's definitely an intermolecular force, right? But it doesn't really have to do with solids, liquids, and gases. Right? So molecule ion attraction or ion dipole attractions are why ionic solids dissolve to make aqueous solutions. So let's say we have some NaCl solid, right? And this is held together with ionic bonds. So the Na has a positive charge because it's donated an electron to the Cl, which has a minus charge, right? And then we have this whole matrix. Okay, and all of these would be ionic bonds. Okay, so this is all held to those electrostatic attractions, okay, between the positive and negative. Well, water is a very strong dipole. And it interrupts the ionic bond or the electrostatic attraction and surrounds the ions in solution. So if we were to take this solid NaCl and put it in water, okay, remember water has this very, very abnormally large dipole. This side is very, very, very negative, and this side is very, very positive. All right. Well, this negative and this positive, it interrupts this electrostatic attraction force. And it pulls these ions out of the solid and dissolves them into solution. Right? So this ionic bond and this ionic bond would be broken, and the Na would go into solution. Now it's got a +1 charge. And then my water molecules completely surround it in solution. We've already done this. Same thing with the Cl. And the Cl is pulled out, and it's got a minus charge. So this time, the H's of the water molecule would be in. But it, again, would be completely surrounded in solution. This is called molecule ion attraction because it's an intermolecular force. Okay, it's an intermolecular force between a molecule. So here's my molecule. And an ion. So there's an attractive force between those. Right? It's also called ion dipole attraction. And it's the same thing. Chlorine is an ion, water is a dipole, so you have an ion dipole attraction. Right? So this is the fourth intermolecular force. It's just a little bit different than the other three. So this is the one that people forget that is actually an intermolecular force. All right. So those are the four intermolecular forces that we need to talk about. And the next thing we're going to go into are the physical properties of liquids. So there are a lot of different properties of liquids, and it has a lot to do with intermolecular forces, right? And we're going to start running through some of those. And the first one we're going to talk about is surface tension. So liquids tend to form droplets. So let's see, how do I want to do this? Let's say this. Molecules in the interior of the liquid are attracted equally in all directions. So if I have a molecule on the inside of a liquid, it's got attractive forces all around it, right? So it's got an attractive force that way, it's got an attractive force that way, it's got an attractive force that way, and it's got an attractive force that way. So we get this equal attraction in all directions. This is if it's in the middle of the liquid. Well, what if it's at the surface? So let's say that we have a surface between liquid water and air. Okay, so here's my particle. If this is air up here, okay, there's no attractive force here. So now there are attractive forces on either side of the molecule, and there are attractive forces down, okay, towards other molecules on the inside, but there is no attractive force in here. So because of this, there is a net inward force on molecules that are at the surface. So now, that does something to our liquid. So molecules at the surface have a net inward force pulling the molecules in. Now, because of this, it wants to make the smallest possible volume. And the smallest possible volume we can make is a sphere. So for a given volume, a sphere has the smallest surface area. So the net inward force makes the molecules pack as close as possible to make the least surface area and that shape is a sphere, which is why we get droplets. Okay. So let's think about this in terms of rain. Okay. If you actually look at rain as it's falling, okay, it's spheres. Okay, it's in a sphere. Well, why does it take this sphere shape? Why don't we get like, okay, why don't we just get oblong, something like this? Raindrops. Or, I don't know, something more like this. Well, it's got to do with that force on the molecules at the surface. Okay, so what's going to happen, remember, so if this is a water molecule, okay, if that's a water molecule and there are lots of them, the ones at the surface, okay, they have a net inward pull. So the one next to it is going to pull inward. The one here 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 is going to pull inward. And as it's pulling it inward, it's making this sphere. And they pack together as tight as possible because they're all being pulled in, right? Which gives us this sphere or droplet shape. Now, our surface tension, okay, our surface tension has to do with this inward force and this force right here between these surface molecules. That's our surface tension. Now, you've seen this, I'm sure. Let's see. Oh, I know. Have you ever taken a penny? Okay, you've taken a penny. You know how it has a little edge here all the way around it? Okay, so this is a penny. If you start adding droplets of water, okay, if you start adding droplets of water, you'll end up getting a mound of water like this. You end up getting a mound of water. right? And the reason that this will do this is because H2O has strong surface tension. Well, why does water have strong surface tension? Well, its intermolecular force is hydrogen bonding. So we can get this. You've probably, I don't know if you've ever tried this, but if you haven't, try this at home. Take a glass, okay, take a glass from the cupboard, and I want you to fill it with water. And if you're careful, when you get to the top, you can actually fill it above, and I can't really show that here, but you can fill the water above the cup, just a little bit. You can't do it very much, but you can actually fill it above the cup because of the strong surface tension of that water. Right? It's pretty cool. So if you haven't ever looked at that, right, go to your kitchen, grab a cup, fill it up, and then I want you to fill it up just up over the ridge so you can actually see, okay, that water surface above the height of the cup. Right? So there's a relationship between surface area and surface tension and intermolecular forces. The stronger the intermolecular force, the stronger the surface tension. The stronger the intermolecular force, the stronger the surface tension. All right. Let's talk about our second property, and these are called cohesive and adhesive forces. So let's talk about a cohesive force. So when we're talking about cohesive forces, we're talking about forces of attraction between identical molecules in a liquid. Versus an adhesive force. So an adhesive force is the attractive force between liquid molecules and a surface. Now, we can actually see these in a couple different things. All right, so let's say that we have a graduated cylinder. And our graduated cylinder is glass. Okay, so this is a glass graduated cylinder. All right, when we pour water in, at the surface, okay, what do we get? What do we get that? What do we get, you know? We get this little curvy thing. Okay, who remembers what that curvy thing's called? Okay? Well, this is what's called a concave meniscus. Now, where would we read the meniscus here? Well, you read at the very bottom of this meniscus, right? But why? Why do we get this concave meniscus? Well, there are two different types of forces here. There are cohesive forces, and those cohesive forces are the attractive forces between the water molecules. And then there are adhesive forces. And the adhesive forces are the attractive force between the water molecules and the surface, right? And in this case, it's the glass. Now, if we look back to our water droplet, these are all what type of force? These are all cohesive. It's all between the same molecules. So if the cohesive forces are strong, we get this convex kind of curve, right? But we don't get that, all right? So we don't get this curve. It's reversed. It's the other way. Okay? What this is telling us is that this adhesive force between the water and the glass is stronger than the cohesive force between the water molecules. So what happens is that adhesive force is pulling these water molecules up the side of the glass, and you end up getting a concave meniscus, right? So the adhesive forces between the H2O and glass are greater than the cohesive forces between the H2O molecules, which is why we get this concave meniscus. Now, that's one example I want to give you. Now, I know we don't look at mercury thermometers. We're not even supposed to have mercury thermometers in school. All right, but if you were to ever look at a mercury thermometer, it would look like this. Okay, so here's my thermometer. Here's my bulb. Here's my thermometer. And this is a mercury thermometer. Well, if you look close to a mercury thermometer, where you read the temperature, it actually does this. It does the exact opposite of that guy. This is what's called a convex meniscus. Now, what does this tell me? When we see this, what is it telling me about the cohesive and adhesive forces? Well, since we're getting this convex meniscus, that tells us that the cohesive forces of mercury are stronger than the adhesive forces between mercury and the glass. Okay, so there's a net inward pull here, and we're getting this. Okay, we're getting this sphere concave or convex meniscus. So these attractive forces here are stronger than the attractive forces between the mercury and the glass. Right? That's why we get these meniscus. Now, real world, another real world example. Why do we wax our cars? So when there's wax on the cars, what does water do? Well, water beads. Well, what does that tell us if the water is beading? Well, it tells us that the cohesive are stronger than the adhesive. Okay, so the cohesive forces between the water molecules are stronger than the adhesive molecules between the water and the wax. Well, what happens if there's no wax on our car? Well, if there's no wax in the car, the water spreads all the way across the surface. Spreads out over the entire surface. What is that telling me? Well, in this case, the adhesive are stronger than the cohesive. In other words, the water has a strong attraction to either the paint or the metal of the car, all right, and it's greater than the cohesive forces of the water. Now, which one of these do we want? Well, what does water do to our car? It causes rust, right? So we wax the car so that water will bead up and not be attracted, okay, to the car, and it'll actually just bead off and run off the paint and run off the wax. But if we don't have that wax, the water is actually spread out over the surface because of these forces, right? And that sticks to the car and it rusts it faster. That's why you want to keep wax on your car. Okay. All right. Let's talk about viscosity. So viscosity is the resistance to flow of a liquid. The greater the viscosity, the slower the liquid will flow. Okay. Perfect example is the difference between pouring water and pouring maple syrup. If we pour water, it pours right out. It goes really, 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 really fast. All right, so it will flow really well. Maple syrup, okay, when you pour maple syrup, it pours much, 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 much slower. Okay, this one has a much higher viscosity. Okay, maple syrup would have a much higher viscosity than the water. Now, for a liquid to flow, the the molecules must slide past each other. The stronger the intermolecular forces, the more viscous, viscous, a liquid is. So what this is telling us, and we go back to our example over here, water has pretty strong intermolecular forces, but maple syrup's intermolecular forces are even stronger. All right, how do we know? Well, it's got that really high viscosity. Okay, it's that really, really thick liquid. Okay? So it's really hard for these molecules in the syrup to slide by each other and pour or flow. Now, does temperature have anything to do with viscosity? I've got a question for you, just for fun. How many of you have ever been to IHOP? I have. My wife and daughter love IHOP. All right, not a big pancake fan, but whatever, I'll go with them. All right, so where do they leave their pancake syrup? Where do they leave that pancake syrup? Do they bring it to you cold? Because it'll last longer if it's cold. The answer is no. Okay. They leave the syrup on the table so that it's room temperature. Why? It's easier to pour. Okay, it's much easier to pour. Okay. Now, ready? Viscosity of liquid increases as temperature decreases. So remember, in a liquid, the particles are vibrating and rotating. The faster they're rotating, okay, and vibrating, okay, they spread out. They keep spreading out. Not much, but they spread away from each other, which decreases the intermolecular force. If the intermolecular force decreases, it pours more and more easily, right? So as we decrease the temperature of the liquid, they rotate and vibrate slower and slower. They get closer and closer together. And remember, as they get closer together, those intermolecular forces get stronger. It gets harder for those particles to slide by each other, okay, which means it's harder to pour. All right, let's deal with one more for today, and that is what's called evaporation. So evaporation is when liquid in an open container is converted to a gas. Right? This is a spontaneous process. It's a spontaneous process, which means evaporation will happen on its own. Okay, so now, let's say that I have an Erlenmeyer flask. And in my Erlenmeyer flask, I pour in here some water. Now, there are water molecules right here at the surface. Okay, right? So we have a surface tension. Now, I take this water and I stick it back there in front of the windows. And over time, one of these water molecules, it'll gain enough kinetic energy to break away from the surface and become a gas. And it'll be lost up through the top. And then another one will gain enough kinetic energy, break away from the surface, and become a gas. Now, where is this energy coming from? Well, remember, temperature of this liquid is an average. They don't all have the same exact amount of energy. Some have more, some have less. Okay, at the same time, okay, the air above it could have more or less energy. So these amounts of energy that each one of these molecules has is always changing. All right, so at some point, this guy right here might get some extra energy. It might have enough to break away and become a gas, all right, and it's all lost. And eventually, over time, okay, this will evaporate and disappear and become a gas. All right, so let's write a few things. Molecules with enough kinetic energy will break away from the surface and become a gas. All right. So if I take this and stick this in the back and I just let it sit back there, it's going to take a long time. Okay, it takes quite a while for this to evaporate and become a gas. All right. Now, what happens if I put this back there and it's a sunny day? Well, the evaporation rate is going to go faster. The question is why? Okay, well, if I put this in the sun, what does it do to the temperature of this? Well, this water temperature is going to be higher, which means more of these surface molecules will have enough energy to break away. So it will evaporate faster. As we increase temperature, more particles will have enough kinetic energy to break from the surface so evaporation is faster. Now, this also has something to do with intermolecular forces too. So if I'm comparing two liquids, the liquid with the stronger intermolecular forces will evaporate slower than the liquid with the weaker intermolecular forces. So temperature plays a role in evaporation. The type of intermolecular forces takes a role. So for example, which one do you think would evaporate faster? Let's say that we have, I don't know, let's say that we have some liquid methane and some liquid propane. Which one would evaporate faster? This one would evaporate faster. Now, they both just have dispersion forces, but this one has stronger dispersion forces, has more of them, right? It's got more hydrogens, okay? So this is gonna take longer to evaporate. It's held down in that liquid longer than this guy. So this guy would evaporate faster. Now, there's one more thing with evaporation. So let's say that I have 3 different containers that all hold the same amount of water. Okay, so let's say that we have a long, skinny bucket. Here's my water surface. And then we got a fatter bucket. And then we have a really short but wide bucket. Okay, so they have the same amount of water in them. Same liquid. Doesn't matter what liquid it is as long as they're all the same. Which one will evaporate faster? Evaporate the fastest. Which one do you think would evaporate the fastest? Or would they all evaporate at the same rate? What do you think? Well, this one will evaporate the fastest. This one is the slowest. Why? Well, remember in evaporation where the particles are lost from. In evaporation, the particles are lost from the surface. Which one has the most surface area? This one has the most surface area. So there's more places where the water molecules can be lost and become a gas in this large surface area. Right? So the larger the surface area, the faster evaporation will occur. All right, good. All right, I think we're going to stop there for today. There are still some more things that we have to talk about, but I think this is a good stopping section. All right, so have a good afternoon, and we will see you soon.